Welcome everybody. We are going to go over 17.3 and 17.4 today. I want to pick up on where we left off for 17.2, however. So we're going to finish off a little bit of 17.2, but the main part of the lecture will be 17.3 and 17.4. If you remember from Monday, or whenever you're watching this video, from a previous day, we left off with talking about what Q and K are. So remember, Q is referred to as the reaction quotient, and it is the value of products over reactants. We always include the coefficients for the balanced equation as the exponents in the reaction quotient expression. K, the equilibrium constant, it can be set up as an expression the same exact way that Q can. The only difference is that all the concentrations are at equilibrium. So what Q gives us is how close the reaction is to equilibrium. It tells us if we are at the beginning of the reaction, when Q is less than K, if we're at equilibrium when Q is equal to K, or if we're past equilibrium, if we have more products than reactants when Q is greater than K. This is kind of condensed down at the bottom in the QK number line that we drew. When Q is smaller than K, we have an excess of reactants, so the reaction needs to proceed to the right or needs to produce more products in order for it to reach K. And in the opposite case, when Q is greater than K, you have an excess of products and the reaction needs to proceed to the left and produce more reactants. Okay, so how do I evaluate Q and K from given Q and K values of different reactions? So there's two different ways that I can evaluate Q and K from individual steps or from other reactions that I do have available to me. Let's make this a little bit bigger. Okay, so two notes on this. We're going to do a calculation for each note, if I can get this darn thing straight. Okay, first, if an overall reaction is the sum, meaning if you're adding two reactions together or more reactions, the overall reaction Q, or quotient, or K, is the product of the reaction quotients or equilibrium constants. Okay, that's going to make a lot more sense when we look at example question 2. Example question 2 says, what is the equilibrium constant? So I'm looking for K for nitrogen and oxygen reacting to produce nitrogen dioxide. Okay, so let's write that equation at the bottom. That's going to be what we're looking for. We're looking for the K for that balanced reaction. So if I have nitrogen that's N2, it's diatomic. It exists as a gas. And I'm adding it to oxygen. And that's going to create nitrogen dioxide gas. And then if I want to balance this equation, I would have a 2 here and a 2 here. Great. So the reason that these two equations are given is because if I take these two and I add them together, put a little plus sign there, they give me this equation right here. Nitrogen gas, 2O2, and then 2NO2. So the question is, how can I use these Ks right here, these equilibrium constants with respect to concentration, that's that little C at the bottom, how can I use those to get the equilibrium constant for this overall reaction? So we'll say C overall. Okay, the answer lies in that number 1 above, that statement in number 1 above. If an overall reaction, which is this one, is the sum, which it is, I've added these two, of 2 or more reactions, the overall reaction quotient or equilibrium constant. So this number right here is going to be the product of these. So all I need to do is take KC1, multiply it by KC2, and that gives me KC overall. Go ahead, pause the video and do that. And then when you have an answer, press play again and check your answer. All right, this should be your final answer, 2.8 times 10 to the negative 15. K is a unitless value, so you're not looking for units. And also you have 2 sig figs for each of these Ks, so your final answer will also be 2 sig figs. So there is a proof for that. If you take the expressions for equation 1 and equation 2, the equilibrium expressions, and multiply those expressions by each other, you will see that it does give you the expression for Kc overall. Now let's go ahead and go down to number 2. So, previous problem we said that if we add 2 equations together, that's the same thing as multiplying their K values or their Q's. All right, for number 2, if I actually multiply the coefficients of a balanced reaction, I'm essentially taking that factor and it becomes the exponent for determining the new Q or K value. Okay, like I said before, this is going to make a lot more sense when we actually do the problem. Okay, so for the ammonia formation reaction, the reference equation is, reference equation is right here. So I have a balanced equation with a corresponding K and a temperature. The temperature not going to do anything with in the calculation. Just remember that K would change if you had a different temperature. So this is a way of stating we're at constant temperature. Okay, what is the value of Kc for the following reaction? So I am trying to find K for this reaction. Kc overall equals what? Or you can put goal, Kc goal, since we really only have one equation we're looking at. Whatever you want to put, just make it obvious that that's what you're searching for. Okay, so looking at this equation, it is related to this one, but we've done some things to the original reference equation. So I'm going to rewrite it. So we have some space. So we have nitrogen gas plus 3H2 gas makes 2NH3 gas. All right, and I want it to be equivalent to that expression. So what did I do? The question is, what did I do to the reference equation to get my goal equation? Well, notice that NH3 is on a different side, and H2 and N2 on opposite sides. So I basically flipped this reaction in order to get some semblance of this reaction. So the first thing I'm going to show that I do is I multiply this by -1. Multiplying by -1 is the same thing as flipping a reaction. Okay, so that's a factor that I multiplied it by. So I flipped the reaction. But in addition to that, I have a coefficient of 1 here, and I started with a coefficient of 2. I have a coefficient of 1/2. My reference equation has a coefficient of 1. And then I have 3/2 here, but an original coefficient of 3. So you see there's a pattern. That means I had to take this whole equation and multiply it by 1/2 in order to get the goal equation. So what I'll do is take this number and actually say I'm multiplying by -1/2. Multiplying by -1/2 again gives you the following. NH3 gas. Okay, that 1/2 was distributed here. It flipped NH3 to the other side and got rid of that 2. Then I distribute the 1/2 to N2, so I should have 1/2 into gas. Again, the negative just pushed into the product side. Okay, 1/2 into gas plus, and then 1/2 times 3 gives me 3/2 H2 gas. Great, so I was just checking to make sure that that was the correct factor. So looking back at this statement, if all coefficients are multiplied by some factor, the factor here is -1/2. That factor, the -1/2, becomes the exponent for relating the reaction quotients and equilibrium constants. What that is saying is that I'm going to take this reference equation K and raise it to the power of -1/2. Let's do it. So K to the -1/2 is going to equal to Kc of my goal. So that's 2.4 times 10 to the -3 to the -1/2. Go ahead and do that. See what your answer is. And you can hit a quick pause if you need to, and then come back to check your answer. All right, with the correct sig figs, your answer should be just 20 with the decimal after. 2 sig figs. I got 20.4124. All right, so that is how you use reference equations to determine K or Q values for overall equations. All right, let's go on to 17.3 and start expanding on this concept a little. All right, expressing equilibria with pressure terms, relation between Kc and Kp. This is going to be the same as the relationship between Qc and Qp. Okay, so we're just showing how concentration and pressure, or partial pressures, are going to be related to each other and expressing our expressions and giving our expressions, like our reaction quotient expressions and our equilibrium constant expressions. All right, so to understand how Kc and Kp are related, let's do the following. First, let's write the ideal gas law. This should be kind of nostalgic at this point. So that's PV, pressure times volume, is equal to N moles times the gas constant R, the ideal gas constant R, times temperature. All right, let's solve for N over V. So that just means that I'm going to be taking over volume, and then I'll move over RT to the other side. So that cancels, that cancels. What I'm left with is N over V, okay, that's what I have right here, is equal to P over RT. And that's what I have here. Okay, why did I do that? What is N over V? N over V is moles per volume, or moles over liter, and that's the same thing as molarity. Okay, molarity is equal to pressure over RT. So it's just giving you a relationship between molarity, or concentration, and then partial pressures. So how does molarity relate to partial pressures? All right, next step to illustrate how Kc and Kp are related to each other, we're going to set up the reaction quotient based on pressures for the reaction below. All right, so right here I have a balanced reaction. I'm going to set up the reaction quotient expression. So that means I'm looking for Q. Based on pressures, that's QP. Remember, I'm going to do products over reactants, but this is going to look a little bit different because we're looking for pressures. So instead of putting brackets, I'm going to put the partial pressure of the product, which is NO2, and that's going to be squared, again, because this 2 right here. Okay, and that's going to be divided by the partial pressure of O2 times the partial pressure of NO squared. All right, that's the expression. Now I want to set up the reaction quotient based on concentrations. Okay, so let's do the same thing. QC is equal to NO2 squared NO squared times O2. All right, now I want to compare these two expressions to each other, keeping in mind how molarity or concentration is equivalent to pressure over RT. All right. Okay, notice and remember that my molarity or my concentration is equal to pressure over RT. So if I want to make this expression equivalent to an expression that included pressure, so I want to set up the QC so that it includes pressure units. So this is going to be equal to pressure of NO2 squared over RT squared. I'm getting that again from the fact that N over V, or molarity, which is this, is equal to pressure over RT. So I'm substituting in pressure units, and that's going to be over pressure of NO gas squared over RT squared times pressure of O2 over RT. So what I can do is I can separate out my RT terms. So let's move this over a little bit. So this is going to be now equivalent to pressure of NO2 squared over pressure of NO squared times pressure of O2 times 1 over RT squared divided by 1 over RT squared times 1 over RT. So I'm just separating out the terms of RT. So you'll notice that this term and this term do cancel each other. So what you are left with then, condensing this down, is pressure of NO2 squared divided by pressure of NO squared times pressure of O2, all times RT. Denominator of the denominator is a numerator, right? So that's why we have RT on top here. So that means that my QC is equal to this expression. Okay, what information does that give me? Let me make this a little bit smaller. That basically tells me that if I want to get QC and QP equivalent to each other, I have to take my QP and multiply it by RT. So notice this right here, this is my QP expression. So this is the relationship then between QC and QP. If I wanted to get it in terms of K would be the same thing. It would be KC is equal to KP times RT. That's another expression worth mentioning. If I wanted to do it the other way around, I would take KP, and that would be equal to KC divided by RT, or QP equal to QC divided by RT. Okay, so if I wanted to get KP from KC, this is how the expression would look. Okay, so why is this the case? This is specific for this reaction. I'm going to give you a generic or a general relationship between Kp and Kc. The reason that this worked out this way has to do with the balanced equation. Where is my balanced equation? Right here. Okay, if I wanted to calculate, and this makes a difference, the number of moles of gas that have changed. So basically in final minus in initial. I'm going to look at the number of moles of gas on this side, which is 2. I'm looking at the coefficient, minus the number of moles of gas on the left-hand side, which is 3. 2 plus 1 is 3. So that is equal to -1. So my delta N is -1. All right, keeping that in mind, if I want to know what my general Kp and Kc relationship is, it's essentially Kc times RT to the change in moles of gas. So notice if you plug in the change of moles of gas for this reaction, which is -1, what you end up getting is Kp is equal to Kc divided by RT, which is just what we wrote up here. So that change in moles of gas gives us a generic expression, a generic relationship between Kp and Kc that we can use for any reaction. So anytime you're relating Kp to Kc, you always need to take into consideration what the change in moles of gas is. In this reaction, the change of moles of gas was -1. So that would give a relationship of Kp is equal to Kc divided by RT. Remember that -1 exponent brings RT to the bottom, brings it as a denominator. All right, so this is really what you're going to be using for all relationships, for all equations, is this right here. Remember, this is the same for Q. Q and K are set up the exact same. K is just at equilibrium. All right, let's move on to our slide. All right, our last slide, 17.4, comparing Q and K, determine reaction direction. In order to determine which way a reaction will proceed to reach equilibrium, consider the QK line below. So we wrote this previously, but let's write it again. Q, K, big Q. All right. Which way would a reaction, let's say AB, go if Q or if K is greater than Q? All we need to do is look up at the line above, and you'll see that when K is bigger than Q, so Q is smaller, like this, the reaction will proceed to the right. So we would say it would proceed right. It would create more products. All right, number 2, for the same reaction, the equilibrium mixture at 175 degrees Celsius is, it gives concentration for A and then concentration for B. And it's at equilibrium mixture. If the reactant concentration at time 0 is A is equal to this and B is equal to this, which way will the reaction proceed? Should be a little molarity there. Okay, so what I can do is evaluate K and Q and compare them to each other. So let's start off with evaluating K. So K equilibrium is going to equal, and this is my balanced equation, is going to equal the concentration of B to the exponent of 1 over the concentration of A to the exponent of 1, all at equilibrium. All right, so using my equilibrium concentrations, I have 1.2 times 10 to the -4. We're not particularly worried about units here since K is unitless. And this is divided by A, which is 2.8 times 10 to the -4. Let's do the same exact setup for QC. So QC will also be concentration of B to the power of 1, but not at equilibrium, divided by the concentration of A to the power of 1, not at equilibrium. And I'm going to plug in this A and B value. 5.0 times 10 to the negative 3 divided by 1.2 times 10 to the negative, oh, just kidding, negative 2. Negative 2. All right, evaluate those numbers. Take a little pause, then replay the video, not replay, press play again to the video, and check your numbers. All right, so this is what you should get for your rounded values. If they rounded to the same number, then I would suggest you compare them unrounded, but these do show some difference. So these are my unrounded values. So what you want to do is determine which one's larger. So I know that my K is greater than my Q, which is obviously another way of saying that my Q is smaller than K. So you look back at the KQ line up here. Notice that when your Q is smaller than your K, that means the reaction will go to the right. So your answer is reaction, I'm abbreviating, will go right, which is the same thing again as it producing more products, because the reaction has to go to the right to produce products. All right, that is it for today. We will see you again next time, and we'll pick up 17.5.